Hello and welcome to my digital presentation. My name is Tom Veeken. I'm a PhD student at AMOF in the Netherlands, and I'm going to talk to you today about directional quantum dot emission for photovoltaics. Before I start, I would like to thank the organizers for inviting me to give this talk. Thank my colleagues Benjamin, Harshal and Bruno, and in particular my supervisor Albert Pullman. I'm really looking forward to the experience of an online conference at this scale. And with that, let's start. So the title says directional quantum dot emission, and of course, this can be interesting for many applications, but the reason we started looking into directional emission is for the application in a tetracene silicon singlet-triplet downconversion photovoltaics. In such a singlet fission solar cell, you start with a standard silicon solar cell that is augmented by, in this case, a tetracene layer. And this tetracene layer can transmit most of the red part of the solar spectrum, but in the blue part it will absorb light and create singlet excitons. These singlet excitons are able to undergo singlet fission to transform into two triplet energies, true triplet excitons, with about half the energy of the singlet. Now, of course, it would be very interesting for photovoltaics if we could harvest the energy of the two triplets as electrons in the silicon solar cell. That would mean that we could get two electrons for the price of one higher energy photon. However, it's not really possible to directly convert these triplet excitons as electron hole pairs in the silicon solar cell. That is the reason why previous work by Baldo et al. Used quantum dots as intermediaries to make sure that the triplet energy can be converted into electron hole pairs in the silicon solar cell. This conversion can be by direct transfer of the energy in the quantum dot into the silicon solar cell, or by radiative transfer, where the quantum dot emits its energy, and the second one is the kind of transfer that we'll be focusing on in this work. Now, this quantum dot can then radiate, and of course we want emission to be radiated into the silicon solar cell. But you can imagine that there will also be a part of the quantum dot emission that is directed away from the solar cell, and this is of course not the direction that we want to have it. That is the reason why we started working on directional emission of these quantum dots, to ensure that once the quantum dot emits, it actually emits into the solar cell. Now, to study the directional emission, we chose to work with a model system where there is no tetracene on top of the silicon solar cell, but we use the quantum dots in air. Then, if you're looking at the emission profile in a crosscut, you get the following profile, which is on a logarithmic scale, showing that about 93% of the quantum dots emission is already directed into the silicon solar cell. This is taking into account that the quantum dot can have three polarizations, X, Y, and Z oriented, and we obtained this result using FDTD simulations. Now, 93% is a high percentage, but in PV every percent counts, and that is why we want to reach as close as possible to 100%. We're using nanophotonics to try to improve this, and in the next slide I will show you that we can actually, using nanostructures, increase this from 93% to 98% using the same simulation technique. So what we do is we place a nanostructure, a nanocylinder of silicon, on the silicon solar cell in the simulation. And then we model the quantum dot by a dipolar source that is 5 nanometers above the silicon cylinder. Now, this dipolar source will excite many different modes in the cylinder that will then interfere back with the dipole emission. Together, the interference between the modes in the cylinder and the dipole source will alter the amount of light that will go towards the top and the light that will go towards the bottom, and also what is the shape. The goal here is to have almost all of the light going towards the bottom, and we find the optimal shape, the optimal height and the optimal diameter of the cylinder for the downward emission. And if we sweep the diameter on the x-axis and the height in the legend, then we find these spectra that show how much light is going towards the bottom. There is a dashed line which indicates the 93% that we saw on the previous slide, which is the benchmark that we have to beat. And we see that in the range between 300 and 500 nanometer diameter, there are many heights for which there is more light going towards the bottom. And then there is the sweet spot at 425 nanometer diameter and 125 nanometer height, where 98% of the light is going down, which corresponds to the radiation pattern that you saw on the previous slide. Now, we show in simulations that we can beat the 93%, so let's go on, make these cylinders and measure what is the emission of the quantum dots on top. So we use electron beam lithography to pattern a silicon substrate and etch into it with reactive ion etching these silicon cylinders that you see on the right, with in this case the 425 nanometer diameter and closely spaced at about 637 nanometers. You see in the SEM graph that this worked beautifully. All of the pillars are closely together and looking clean and sharp. Then the next step is to get the quantum dots on top, which is a little bit more tricky to get around. Together with Harshal, we found a trick where we take a silicon substrate that is flat and we spin coat quantum dots on top to get a homogeneous layer. If you would directly spin coat the quantum dots on the textured silicon, then you would get most of the quantum dots lying around the rim of the cylinder and not so many on top, while we would prefer to have them only on the top. That is why from this spin-coated layer on the flat silicon, we pick it up with a PDMS stamp by pressing onto it, and then we move the PDMS stamp to the textured silicon sample and we press it down, and by heating the whole sample, the quantum dots will actually detach and attach to the silicon that it was pressed onto. And when we then remove the PDMS stamp, we are left with the textured silicon with quantum dots on top. That then looks like this. This is a zoom-in SEM after the printing of the quantum dots, where we see that the quantum dots have a homogeneous layer and are fully printed on the top of the silicon, but not besides the silicon. Now that we have the quantum dots on the cylinders, we can go measure what is the emission looking like from these quantum dots. On the left, you see an image of the end of a square array of these cylinders that have the diameter of 425 nanometer, but now have a pitch that is twice as large as you saw in the SEM. It's 1275 nanometers, and this is to ensure that we don't get surface lattice resonances in the array, because we want to use the individual me particle modes to make sure that the emission is going downwards. Now what you see in the image here is the dark on the side. This is where the quantum dot layer is printed on the flat silicon, which serves directly on the same sample as our reference measurement. Then there are the pillars that are darker than the substrate that is beside it. The pillars are mainly darker because there are quantum dots on top, and on the bare silicon there is no quantum dots, so the reflection is higher, and this is the light blue color. Then there is one feature, which is this blob here. This is a fabrication defect where the quantum dots got printed on top, and that is why it's also looking dark. Then on this sample in a microscope we can measure the photoluminescence by illuminating the quantum dots with a 532 nanometer laser, and then looking at the emission wavelength as a function of position. Then we get this map that has the same x and y coordinates, but now shows in color the amount of counts on the CCD. We see on the left side here that for the flat silicon there is a homogeneous signal that is quite high, as we would expect. And then on the pillars the emission comes from the pillars, which is higher than that of the bare silicon in between. Then for the artifact we would expect there to be more quantum dots there and not on a nanophotonic structure, so also the PL is here higher, as we would expect. If we then look at the spectra of different positions, we find the blue curve, which corresponds to the flat silicon, which is quite high, and we see that the wavelength is a little bit lower than that 825 nanometer wavelength we used in the simulations. We look at the signal on the quantum with the quantum dots on the cylinders, which has the same spectrum, the red one, but it is much lower than on the silicon. And then we can also look at the spectrum that we find in between four pillars, like here, and we see that it is not completely zero, and this is because our laser spot is a little bit bigger than this area in between four pillars, so it will still excite the four pillars a bit, and therefore we have a little bit of signal, but of course it's smaller as we would expect. Now the thing that we are looking for is that the emission of the quantum dots on a silicon cylinder is less going upwards than when we have it on the flat silicon. We are doing this measurement in reflection mode, of course, and it seems to prove that we have less emission going upwards. But there are two things that we are not taking into account here. The first is that we might have a excitation efficiency that is different, that the cylinder might actually help absorbing the 532 nanometer wavelength of the laser, and therefore the emission might be higher or lower on the pillar. And the second thing is that the quantum dot density might not be exactly the same on the pillar as on the flat silicon. That is why this is not a concrete proof, but at least it's showing a trend in the direction that we expect. To get direct proof, we aspire to make a similar system where we are not working with silicon cylinders on a silicon substrate, which is not transparent at this wavelength, but on a transparent substrate like glass or sapphire, such that we can measure the emission upwards but also the emission downwards, and then we can have a direct comparison that doesn't care about the density or the excitation efficiency. Now, using the system that we have here on the silicon non-transparent substrate, we can look at one more thing, which is the lifetime of these quantum dots. The lifetime of these quantum dots does not depend on the density nor on the excitation efficiency. It only depends on the local density of states that we alter with the nanophotonic structure, and on the quantum yield of the quantum dots, which should be the same for quantum dots everywhere on the sample. Now, if we want to make an estimate of what the lifetime should look like on the flat silicon versus on the cylinder, we can use the same FDTD simulation that we did to design this resonator. In the FDTD simulation, we use a dipole with a constant amplitude, oscillating dipole, and this will result in an amount of power that is generated in the simulation. If we take the inverse of that, then we end up with lifetime, which is the same lifetime as you would measure in a measurement, where it determines how fast the dipole, or the quantum dot in that case, loses its energy. From the simulation, we find this curve as a function of the cylinder diameter at the height that we found at 125 nanometer. We normalize this by the lifetime of flat silicon, which is here set to 1, and then we find that the lifetime can alter quite a bit for the quantum dot on the cylinder. On the same sample, we fabricated not only the 425 nanometer diameter, but also cylinders with 500 nanometer and with 200 nanometer diameter for comparison. Now, especially for the 200 nanometer diameter, we find that the lifetime is much lower than that of the quantum dots on the flat silicon. So if we could measure this, then this would be another indication that the quantum dot emission is becoming directional as designed. Using time-correlated single-photon counting, we can measure what is the lifetime of the quantum dots as a function of position. For the array of 425 nanometer diameter, we here measured as a function of position what is this average lifetime, which is indicated by the color. And for the same optical image 3 times, we have selected 3 regions. One is on the flat silicon, the second is on the array of cylinders, and the third one is only on the cylinder tops. And we see that the colors of the average lifetime is about the same. Then we can also zoom in to the fastest lifetime, which is shown here on the right, where as a function of time we plot the intensity of the counts of the emission. And then we see that 3 curves are here lying on top of each other for the 3 different regions that are shown on the left. These measurements are done by Benjamin and also the analysis, where we show that, as expected from the previous slide, the lifetime should be about the same on the flat silicon versus on the cylinders. However, if we do the same analysis and then we look directly at the exponential fits of these measured lifetimes, then for the 200 nanometer and 500 nanometer diameter, there is a difference between the lifetime on the flat silicon versus the lifetime on the pillars, which is significantly faster. For the 500 nanometer diameter, we would expect a smaller difference, and that is also what we see here in the measurements on the flat silicon and on the cylinders. If we sum these measurements up, then we get the graph here on the left, where the fast lifetime is plotted on the y-axis, and then we have the 3 regions. First is the flat silicon, second is the cylinder's complete array, and then the third one is only on the cylinder tops. And then we see that for the 425 nanometer, the blue one, we see roughly the same lifetime. For the 500 nanometer, we have a slight change, and for the 200 nanometer, we see a significant change. This is, again on the right, the simulated trend, very similar. In conclusion, I've shown you that we can use nanostructures to direct the emission of quantum dots. We can also bring these quantum dots onto a nanostructured silicon surface in a homogeneous fashion, and then we can map the PL signal and the PL lifetime that show the simulated trends. As an outlook, we want to use a similar system with a transparent substrate to measure the upwards but also the downwards emission to make a direct comparison. And in the far future, we would like to integrate this system with a singlet fission layer to use the singlet fission as an excitation of the quantum dots. Thank you for your attention, and I would be happy to answer any questions you have on the forum.